All right, let's dive into one of the most exciting high-stakes races happening in technology today. We're talking about the quest to build a real working quantum computer. And this isn't just about making our gadgets a little bit faster. It's about building a completely new kind of machine that's going to redefine what's even possible. So let me just start with a question to set the stage. Imagine this. What if a computer could solve a problem in the time it takes you to make a cup of coffee? A problem so ridiculously hard that our very best supercomputers today would need, about 10,000 years to even get close. Yeah, that's not science fiction. That is the incredible promise of quantum computing, and it's exactly why companies and even entire countries are pouring billions into this technological Grand Prix. So, how in the world do you get that kind of power? Well, you can't just tweak the engines we already have. You need something brand new, built on the weird and wonderful rules of quantum mechanics. It means we have to go way beyond the simple on or off world of zeros and ones that we're all used to. At the very heart of all our digital tech is the classical bit. It's just a simple switch. It's either off, a zero, or it's on, a one. Simple. But the hero of our story today is the quantum bit, or what we call a qubit. And as you can see, this is a whole new ballgame. A qubit isn't just a zero or a one. Thanks to quantum mechanics, it can be both a zero and one at the exact same time. Now, this mind-bending property is called superposition. The best way to think about it is like a spinning coin. While that coin is spinning in the air, it's not really heads or tails, right? It's kind of both. A qubit is exactly like that, which means it can hold way more information than a boring old classical bit. And this allows a quantum computer to explore a huge number of possibilities all at once, which is really the secret sauce to its incredible power. And believe it or not, it gets even weirder. Qubits have a second superpower called entanglement. This is this deep, almost spooky connection between two or more qubits. Their fates are literally intertwined. So if you measure one entangled qubit and find out it's a zero, you instantly know its partner is a one, even if that partner is miles and miles away. It's this link that lets all the qubits work together in perfect harmony, turning them from individual parts into one massive, powerful brain. Okay, so this is where the race really starts to heat up. See, there isn't just one single way to build a quantum computer. Different teams are betting on totally different designs, different race cars, if you will, and each one has its own set of strengths and weaknesses. So let's take a look at the two leading approaches out on the track right now. First up, we've got the most common approach, superconducting circuits. This is the tech being pushed by the heavyweights, companies like Google, IBM, and Rigetti. They're using these tiny, supercooled electrical circuits to create and control their qubits. The big plus here is speed. Their operations, what they call gates, are incredibly fast, and they can use a lot of the same chip-making technology we already have. But here's the big drawback. These circuits are unbelievably fragile. They have to be kept in these massive refrigerators at temperatures colder than deep space, just to stop them from making errors. Now, the main rival on the racetrack uses a completely different strategy, trapped ions. This is the design that companies like IonQ and Quantinuum are championing. Instead of man-made circuits, they use individual atoms, ions, that are held perfectly still in a vacuum using lasers. Those atoms are their qubits. So this presents a really fascinating trade-off. Trapped ion qubits are way more stable, and they have what's called higher gate fidelity, which is just a fancy way of saying their calculations are much more accurate. And here's the kicker. They can operate at room temperature, which could make them a whole lot easier to scale up. The traditional downside? They've been slower, though that speed gap is closing really, really fast. So, with these different engine designs in mind, let's actually meet the teams in this Grand Prix. The field is this incredible mix of giant tech companies, really ambitious startups, and some super specialized hardware outfits. Okay, this chart gives us a fantastic snapshot of the racetrack. Over in the superconducting corner, you've got giants like IBM, who are gunning for a machine with over 1,000 qubits, and of course Google with its famous Sycamore chip. Then, in the trapped ion corner, you've got key players like IonQ and Quantinuum. Now, pay attention to the qubit numbers. It's not just about how many you have, but how good they are. We'll get to that in a second. And then you've got wildcard players like D-Wave, which uses a totally different method called annealing that's really good for one specific type of problem. It is a crowded and fascinating field for sure. But here's the thing. It doesn't matter which car a team brings to the race. Every single competitor faces the exact same massive hurdle. You can think of it like a treacherous, oil-slicked track that threatens to send every single car spinning out of control. And that obstacle is noise and errors. The main villain of our story has a name: quantum decoherence. Remember those super delicate quantum states like superposition? Well, it turns out the slightest vibration, the tiniest change in temperature, any little disturbance from the outside world can cause that qubit to just collapse. It forgets all its quantum information and goes back to being a simple 0 or 1. This decoherence is the #1 cause of errors in quantum computing. And that brings us to maybe the most important point of all. Not all qubits are created equal. You'll hear companies brag about their number of physical qubits. That's just the total raw number of qubits they can cram onto a chip. But the number that really matters is the number of algorithmic qubits. Think of it like this. Physical qubits are your entire sports team roster, including everyone on the bench. Algorithmic qubits are your star players, the ones you can actually put on the field to win the game. They are the stable, useful, error-corrected qubits that can actually get the job done. Now, you might hear a company boast about a gate fidelity of 99.9%. That sounds amazing, right? It means their operations are correct 9,999 times out of 1,000. That's an A+ in any school. But here's the catch. A real quantum calculation doesn't take thousands of steps. It takes millions or even billions of them. And with that tiny 0.1% error rate, an error isn't just likely, it's a mathematical guarantee. Your final answer will be total nonsense. This is why creating good quantum error correction is the absolute holy grail for this entire industry. It's the challenge everyone is trying to solve. So, keeping that massive challenge in mind, what's the actual finish line everyone is racing towards? What does it even mean to win this quantum Grand Prix? Well, it comes down to a concept called quantum advantage. Quantum advantage is the tipping point. It's that moment when a quantum computer finally proves it can solve a real-world, commercially important problem better than any classical supercomputer we have. Better could mean faster, or cheaper, or just more accurate. This is the moment quantum computing moves out of the research lab and into the real world. And the prize for being the first to cross that finish line? It's huge. We're talking about a new tool to solve some of humanity's hardest problems. See, quantum computers are naturally amazing at simulating nature at the molecular level, which could totally revolutionize how we discover new medicines and design new materials. They are just born to solve these kinds of problems. The impact is going to be felt pretty much everywhere. In finance, it could optimize trading strategies worth billions. In healthcare, it could help design life-saving drugs in a fraction of the time. In manufacturing, it could create amazing new materials for things like batteries. It could supercharge AI and, for better or worse, it could probably break the encryption that keeps most of our digital world secure today. And look, this isn't some far-off dream. If you check out the roadmaps, you can see how fast things are moving. Next year, we're expecting to see new types of chips and major players targeting 64 of those useful algorithmic qubits. By 2028, some companies are aiming for over 1,000 of them. The whole industry is pushing hard to hit what they call broad quantum advantage by the end of this decade. The race is getting faster every year. And what's really wild is how close we might be for certain problems. As this quote suggests, we might not need millions of perfect qubits to start seeing an advantage. Many experts believe that a stable, error-corrected machine with as few as 70 of those algorithmic star player qubits could start to beat our best supercomputers at some very specific, very valuable tasks. So the teams are on the track, the engines are getting more and more powerful, and the challenges are still huge. But the prize, well, it's nothing short of revolutionary. The race is on, and it leaves us with the biggest question of all. Who is going to build the computer of tomorrow? And are we ready for the world that it's going to create?